Hello, my name is Cayden Peters. I work with Dr. Weinberg from the physics department, and I'm presenting the impact of dynamical tides on the light curve of the hot white dwarf binary system KY964. So basically what we're studying here is this unusual binary star system, which consists of an A-type star that's about double the mass of the sun, and it's being orbited by this hot white dwarf star. And what's especially interesting about this system is that it has a very short orbital period of about 3.3 days, which means the two stars are very nearly touching each other in this orbit. And because they're so close together, the tides are very strong, and the A-type star gets highly distorted into this sort of football shape, as you can see at the bottom of this poster down here, which is called the equilibrium tide. The tidal distortion causes the brightness of the star to vary with time over the course of the orbit, because as the stars orbit, sometimes we're looking down the long axis of the football, and sometimes we're looking down the short axis, so you're getting a variation there. Now, the Kepler Space Telescope detected these changes in brightness, and a 2019 paper by Wang et al. Showed that the observed tidal distortions could help constrain important properties of the system in detail. For example, they used them to measure the mass of the star and the radius to a high degree of accuracy. Now, while the Wang model could explain many features of the Kepler light curve, it significantly underestimated the amplitude of distortion by about 45%. And this is where our study comes in. We're investigating whether this discrepancy is attributable to the fact that the Wang model does not account for the tidal excitation of waves within the star, which is called the dynamical tide. Now, tides can excite waves similarly to how a hammer striking a bell excites waves in the bell, which we pick up as sound waves. It's the same idea for the stars and for the orbit of the tidal force. So to test this idea, we first construct models of the A-type star using the MESA stellar evolution code, we take these models and feed them into the gyre-tide stellar oscillation code to determine the expected amplitude of tidally excited waves within the star. An example of these waves that can be excited is shown in this figure 1 here. Now this figure shows the radial tidal displacement and the flux perturbations versus the forcing frequency in units of orbital frequency. So each of these spikes shows a frequency that can resonate with the A-type star. Now, after constructing these stellar models, we wanted to make sure that we could reproduce the Wang results that ignore the tidally excited waves, which we look at in figure 2 here. So this is the equilibrium tide. The black line here shows the Wang model. The Wang model's equilibrium tide, and the red line shows the other model that we used to compare. And you can see there's very good agreement here. We attribute these small differences to differences in the way that limb and gravity darkening were treated between these models. Now, once we knew that we could reproduce the Wang model, we used the gyre code to see if tidally excited waves could have significant enough amplitudes to explain this 45% discrepancy. And since the amplitude of the waves is sensitive to the mass, temperature, and metallicity of the star, we need to construct many MESA stellar models and feed them all into gyre tides. This will give us the probability distribution of the wave amplitudes, and you can see this in figure 3. So on the y-axis we have again delta F over F, the flux perturbations, and on the x-axis is again sigma over omega orb, but we've zoomed into k equals 2 this time because since the orbit is circular, there's not a range of frequencies that could potentially be excited, but just one at k equals 2. And if we just look at k equals 2, we can see that we can see where all these curves intersect with k equals 2, and we can get an idea of what the likelihood is that a given model will have a given flux perturbation amplitude by seeing where it, intersects with k equals 2. And we are currently computing this distribution of wave amplitudes, and once we have it, we'll be able to say how likely it is that tidally excited waves can explain the discrepancy between the Wang model and the Kepler observations. And if it does, it will provide additional insights into the properties of the A-type star and how waves are excited and propagate within such stars. Thank you.